Good morning. Today we're going to start actually lecture 9. We're going to continue on a chapter that deals with MATLAB functions. We will, today we're just going to do a couple of examples where we will be using the custom made or user-defined functions. So we're going to do actually a couple of problems that really will help in explaining those functions and how they work and how we can call them if it is from a script file or from a command window. So let me share my screen and start doing a couple of problems. I'm going to go back to one of the problems that we skipped in the in-class problem set that I think it's in-class problem 2 that is uploaded in your let's take here. All right, so this is, yeah, if you go to in-class problem 2 that is uploaded in on Canvas, you'll see that there's this problem that we never solved. It is a function problem that we'll be doing. There's also another problem that we'll also be tackling later on when we cover the if and if else and else statements. But for now, we're going to do this problem, and we're going to also do other problems as well that are already uploaded in Canvas. So let's read this problem. Let me enlarge this here a little bit. So we have Manning equation can be used to compute the velocity of water in a rectangular open channel flow. So this is something if you take fluid mechanics and cover open channel flow, the Manning coefficient or Manning equation will be a defining factor in evaluating the height and the velocity and the volume flow rate of an open channel flow like a river, creek, or others. When we talk about open channel flow, it's flow that is confined in all surfaces except the top surface. So Manning coefficients and Manning equation is one of the most important parameter that we deal with in open channel flow. So we're not going to go so much into, like I said, in the physics of the problem. We just want to make sure that we solve this equation using a function equation. And if you notice here, he defines U as the velocity meter per second, S is the channel slope, N is the roughness ratio, and B is the width, and H is the depth. So so we are to actually find the velocity, and we're given again all these again the slope of that channel and also the roughness coefficient. Again, B is the width and H is the depth. So if you look at the table, it's given us a list of 5 values of N, S, and B, and H. So what we want to do, we want to write an M file that computes the velocity for each of these channels and enter these values into a matrix where each column represents a parameter and each row represents a channel. Have the M file display the input data along with the computed velocity in a tabular form where velocity is the 5th column, including the heading on the table to label the columns. So this is great. So what we're going to do, we're going to use matrix, and we're going to use also the function, a user-defined function to calculate this velocity. And also, we want to make sure that we tableize that with all the headings. Okay, so let me scroll this to the left, and I want to open MATLAB here. Let's see. So what I want to do here, I want to start a new script with a function name. I'm going to save that function. And what I want to do, I will call this function in the command window. So I'm going to go with a new script here. And remember, when we start a function or create a function, the name of the file should be saved with the same name of that function. So if you were to try to call it from the command window or from any other script, MATLAB will know that, okay, this function is saved, and MATLAB will execute the function and give you the output. So let's start with the function. I mean, we need one output. We have only one output, which is u. And as far as the input, definitely we have 4. If you look at this, we have 4 inputs. We have N, S, and B, and H. Now, if we were to write this as individual independent variables, we can definitely have the input variables as N, S, and B, and H, and that should be solved. But he's asking us a little bit different. He said that write this as a matrix. So what we're talking about, that N and S and B and H is a part of a matrix. And each value of this will be a matrix index. And so actually, in fact, what we have a one, if you look at this table as a matrix, you're going to have only one input variable. Okay, so this is not the ideal way of solving such a problem, because if you modify the matrix, you're going to have to really modify your function. But that's what he's asking, so we're going to have to do whatever he's asking. So the first thing we want to do is we're going to define the function, and I'm just going to call that function Manning, and just do of A. Okay, and so the Manning is the function, and I'm going to do in here. A is that matrix because it's 5 by 4 matrix. So what is A? All right, so we're gonna have to put A, which is he's mentioning that we want to create an additional column. Remember, we have N, S, and B, and H. So the additional column, which is with index, again, all the rows with column 5, right? That's what he wants, and that's gonna be the U, and it is equal. I'm just gonna put the equations in there, that equation here. It's gonna be a square root of, so it is SQRT of S is gonna be the second column. So let me open this, will be equal to A, and also open the parentheses, second column, right? Let me close that. So that the square root of S divided by, and make sure here, because it is an array, actually a matrix, so I'm going to just do the dot in there. And N is actually the first column, so it is of A, so A, and so again, the column, comma, and sorry, colon, and this will be 1. Okay, and so that should do that. So that is okay. So that's square root of S divided by N times. So don't forget, when you do the times, we want to make sure that you have the dot in there. And all right, so that is, I'm going to open a 1. B is the third column, so it's B of, again, column, and then column, and then you're going to have, again, B is 3 here, right? Times, again, don't forget to put the dot in there because it's an array multiplication. And H is the 4th column, right? If you look here, this is the H is the 4th column. All right, so that is, let's just do this one here. Also column, comma, and 4. So that is, so it's A3 times 4. And then what we want to do is we want to divide that. So let's divide that to on, what is that? B. Yeah, B, which is also, again, it's A3. So just, yeah, B. So let me open a, let me actually do the division here and open a parenthesis and A, again, column A3, that's B, plus 2 times, don't have to put a dot in there. Let me just make sure. All right. So 2 times A, and I'm just going to do the 4th H, which is, again, column, 4th column would be 4. And I'm going to close the parentheses for the denominator, and also another parenthesis for the parenthesis that I opened right here. What is that? This one here. And remember, these are going to be to the power, so it's going to be dot to the power caret, right? And 2/3, 2 over 3. And what I want to do, let me do this. Let me suppress that. Now, so that is the equation, right? That is the equation of A. So this is the equation. This is what's going to give us in that 5th column. But now what we want to do, we want to F print this. So we want to F print because we want to stabilize those. And first of all, we want to do the titles. So the titles will be, let me do that, open parentheses and comma, backslash n, and then we, yeah, let's do n here to the, and then s, just putting the space in there, and s, let me do this one as a B, I just do it too much, B, and also H. Okay, so that's H. Here we go. And then we're gonna do U at the end because that is the 5th row, and just to the backslash and then close that one, and then close the parentheses. And then what we want to do is just do this in my column. So this is that will take care of the title that we want, and then we'll do now the F print P. The solution and the values. So fprint tf, let's do this here. Print tf, and then now we want to here fprint tf. I think I did an extra t here. No need for that. fprintf, and then we open the bracket. Let me open a apostrophe, and we're gonna do percentage 8 0.3 f, and so that will be for n, and then you have percentage. Let's just do percentage. What is that? Percentage 8 0.4 f, and then we do percentage 10.2 f, and then we do percentage. This is how we are placing these values with the significant digits as well. So this is also 10. I'm going to do also 10, also dot 2f, and then for the last one, yeah, let me do the last one, which is percentage 10.4 f, and I will just do backslash and close that one, and then we'll do a and also the apostrophe, and then we close the parentheses and we'll do a semicolon. So this is how we want our table to look like. And I'm just going to save this. I'm going to call this. Now, you got to be careful here, because when we try to save, so let's do that. Let's save as. Automatically, MATLAB will call this for us as Manning. So do not change that. Leave it, because it will go every time it sees function. It will always name that as the file, our defaulted file. So we're going to definitely keep that. So now, since we have this, let's call this program and let's see what we get, because this is already saved. So I'm going to call it from the command window. So let me open that one and maximize that. And I'm going to call that. So what I want to do first, I'm going to enter A, the values of A, the one that I have in here, right? Remember, this is 4 by 4, 5 by 4 matrix. So I'm going to enter that. So A is equal. Let me open a bracket. So it is 0.036 and 0.0001, 10, 2, and then semicolon. This is the first row. Then you have 0.02, 0.0002, 8, and 1, and also semicolon. This is the second row. Third row is 0.015, and then 0.0012, 0.0012, and you have 20, and you have 1.5. So that is the third row. Fourth row. Fourth row will be 0.03, and then you have 0.0007. Then you have 25 and 3. Last column, last row will be 0.022, 0.0003, 15, and 2.6. And I'm just going to close that and do suppress the. So let me just do that here. So that is the that's A. All right, let's just make sure that I have everything in there. So that's 4 elements, another 4 elements. Okay. 10 and 2, 0.02, 81, 0.015, 20. Okay, looks good. Looks very good. Okay, so that is A. We define A. So now what we want to do is just go and call that function. And the way we're going to call that function, just type Manning and Manning of A. And that should give us something here. So let's hit OK. All right. Well, something with that we did that was not right. So let's go back to the Manning function. And there's something that we did that did not make any sense in there. So let's see what we did wrong. All right. Actually, what we want to do, we want to go through the yeah, I think I made a mistake. I was missing an F in there. So let's go back to the, let's minimize this one here and go back and see what we did here that is wrong. So F see here, I'm missing an F in here. And that is why it is not printing those. So let me save that again. And I'm gonna go back in there, command window, maximize it, and I'm gonna actually, instead of retyping Manning A, all I do, I just use the up arrow and then choose, it gives me that command because it's recorded, and then I just, all I have to do is calculate that. So, oh, there's something is not right. I mean, we've, that's not how I want it to look. So something is a little bit off. So N looks very good, but somehow it is mixing those numbers in there. So something that we did that did not really do the whatever we ask to. So N, let's see what was the mistake here. So we have 0.036, and it looks like it is overlapping these, like for example, this is the calculation for you and it's supposed to be in there. So something with our setup did not work. So let's go back and see what did we do wrong. It looks like the first, the titles worked, but something that is not working as far as, yeah, it looks something is not working with that setup, table setup. So let's go back, let's minimize that. Let's see what we did wrong. So 8.4, so let's see if we can go back a little bit here. And maybe we overlapped it a little bit, and that's, just do this one here. I don't know if it is gonna solve the problem. Let's try. Let us save this and go back to the Manning here and see if it's gonna work. It is still giving me that problem. So something. Oh, Here we go. I'm missing, if you look here, I'm missing that percentage. So does give me where the problem is in that line 4. So that percentage cannot miss. So let's now save it again. And let me do this and rerun that. And I don't know. Okay, now I guess we got what we want. All right, so remember here there was a percentage for 10.4F. It did not take it. So if you look here, this is exactly what he asked us to do. So look, N, this is the first row, first column, S is the second column, B and H, and U, this is what we calculated, which is, this is what we asked MATLAB to do, to actually place those in the fifth column in there. Again, this is not the best way of writing a program like this, especially when you do a function. It's great to have a function with those 4 variables, input variables in there, because if you ever change the setup of your of MATLAB of your matrix, then you won't affect your results. But this is a great example. So again, let me just do see here and rerun it again, just to make sure that when you try it yourself, make sure you get the same answers, because these are the right answers. And if you really want to make sure that what you're doing is right, just do one calculation for one row, and you will see that you will get that velocity pattern. Okay, just do for the first row, and then you'll see if what you're doing is correct. All right, so this is it. This is the function, Manning function, and again, you can just take a look at this and save it. Just take a snap on it if you cannot catch up with me, but please do that on your own as well. It's nothing wrong if you made a mistake. If you make a mistake, we are all gonna make mistakes when we write programs. Again, the beauty of MATLAB that it's a self-debugger. It will tell you where's your error, where it exists. For example, it told me first at line 3, and I went to line 3. I fixed it. Then it tells me line 4. There's a problem. It was a percentage sign that I missed. So just be careful when you write. Try to slowly write your program so you don't make a mistake, but it doesn't mean that you are not going. And don't panic if you see an error that says, oh, it doesn't work. It doesn't matter. You're gonna it's a process, it's a iteration, so you're gonna fix it, you're gonna change it, modify it to make it work. It is okay. It's a process like that. All right, so now what we're gonna do another types of problems also. It is also something to do with a function. So let's read this problem here. An object thrown vertically with a speed v0 reaches a height h at time t. Now h is given, again, v0t minus 1/2 gt squared. Again, it's a parabolic equation. This is something that you probably learn most likely in dynamics or physics. Write and test a function that computes the time t required to reach a specified height for a given value of v0. Now, the function's input should be h, vz, v0, and g. So these are the input variables. And again, h will be the output variables. And test your function in the case of h equal 100 meter, v0 50, and g is 9.81. So we want to find the time function for that. So there's a couple of ways of doing something like that. But again, the output variable should be the time. and there's input variables that consist of the height, the v naught, and also g. So that would be our function. And what we want to do at a value or specified value of h, we want to find what is the time. Now, if you remember, and if you look, this is a parabolic function. I don't know why I have this one here. All right. So this is a parabolic function. So you're going to have two values for time when you solve this parabolic function. And what we want to do by doing that, we are going to expect those two values of time. And the reason why, because you have, when you're throwing this object or ball vertically, you're going to have one time when you're going upward and another time when you're going downward. So you just need to be, very careful when you're interpreting and explaining your results. Why we're getting two values of time, and we expected, if you want to solve this, you can definitely solve this. It's just a quadratic equation that you can solve using your calculator or by hand. But the beauty of MATLAB that you can always change these values and come up with a time. So if you change the v naught and change also the height, all you have to do is just enter those new input variables, and then you will get your time. All right, so let's do that. All right, so let's see here. And we are going to start a new function. So all right. So these are the values. All right, so new function. So we're going to start a new script, and we're going to start always with function. This is our first. I mean, you can do some explanation and explain the problem. It's you're throwing a ball vertically and explain. You can do the percentage sign and do the explanation. Or actually, you can actually copy and paste whatever you have and just put percentage sign. This way, we understand the problem, what we want to solve. So this is function. We want to find, this is the output variables, and then we'll do equal time. That is the function. Let me just do this one here so you. So the name of the function is time, and our input variable is h. H is the height, and also v naught, right? And also g, which is gravitational acceleration. Okay. So that is these are the input variables, and what we want to do is compute again the time to reach charge with initial velocity. That's what we want to do. So I'm gonna do, and in order to do that, all you have to do is just choose the roots equation, because if you just do this here, you see, you're gonna have, you can rewrite this one here as 1/2 gt square minus v0t minus plus h is equal to 0, right? So this is a quadratic equation. All I have to do is just solve for that t, and if you want to do this, you can just use the roots for that one, right? The roots of this one. And how do we write this polynomial function? This is the coefficient for t squared. This is the coefficient of t, and this is the coefficient for t to the power 0. So So it is actually all you have to do is just find the roots for this equation. So what is, let's come back in here and find the roots of that. Roots of, when you do the roots, you just want to open a bracket, a parentheses, and the brackets for p, which is in this case, the first one is, what is it, 0.5 times g, right? And also the second term will be minus v0, so let's just do this one here, minus v naught, and the third coefficient will be h. And we're going to close the bracket and close the parentheses. And I'm just going to end it. And okay, always when you start the function, you can put end in there, and we'll solve that. Let's save that one. Let us save. Again, when you do save as, it will give you the time as a defaulted name, and just keep it, don't change it. And I'm gonna go back in here, and I'm gonna call that function time, and I'm gonna put those input values. It's down as 100 for the height, and v naught is 50, and for the gravitational acceleration is 9.81. Right? So, and all we have to do is just put enter, and you're gonna get, when you press enter, you get two values, 7.46 and 2.76. So how do we explain this? You know, when you're throwing this ball upward at certain h, when you're going upward, you're gonna, that 2.73 seconds will reach when you're ascending, and when the ball is or that object is going down and descending, that will be the 7. It's going to take 7.46 seconds. Okay. Now you might tell me, oh well, I could have solved this using calculator or using my hand. Yes, you can, but you know, let's suppose that you change that height in there. You don't have to redo the calculation. All you have to do is just call back that function and change the input variables. If you change the initial velocity, it's also the same. So just you know, you need to you know, use that not because you cannot do it another fashion, because it's more it's simpler, and it is you know, it just saves you a lot of time. So especially when you have this function is a part of a bigger script, so you don't have to stop and do the calculation. It does that for you, and then you can, as you're gonna say, you can globally save those results in there. All right, so that is one of the problems on that. So I want to do another problem also. So let's enlarge this one here. All right, so this one here, let's read this one. This is interesting problem 2. We have a water tank consists of cylindrical part of radius r and height h, and a hemispherical top. I mean, the tank is to be constructed to hold 600 cubic meter when filled. The surface area of the cylindrical part is 2 pi r h, and its volume is pi r squared times h. This is the cylindrical part of that tank. The surface area of the hemispherical top is given by 2 pi r squared, and its volume is given by 2 pi r to the power 3 divided by 3. Now the cost to construct the cylindrical part of the tank is $400 per square meter of surface area, and the hemispherical part costs $600 per square meter. Use the F-min BND bound function to compute the radius that results in the least cost. Compute the corresponding height h. Okay, so two things. We have a so this is what we have. Let me draw this tank here. So we have a tank that has a cylindrical part of it, and it has also a semi hemisphere part. This one right there. So the semi hemispheric part is going to look something. You know what? Let me do this here. Let me do this with a red. So you're going to have so you're going to have something also like that. Okay. So this part, the one that we wanted to solve. So this is R. Maybe I just do this. All right, so again, that is R. And what else is he giving us? He's telling us that we actually want to optimize the price when we build such a tank. I mean, H will be also is the height of that tank. So we're gonna say that H it starts from here upward. Okay, so that is H, and so a couple of things we want to do. We want to use the fmin_bound function to compute the radius. Okay, which is the R optimum, the optimum radius that results the least cost. So we're gonna do R optimum. We want to find that with minimum cost. Okay, and he's given us the price for each square meter for the surface of the hemispherical, and also the square meter of a surface area, right? So have to be pretty smart on this when you want to do your program. And then once you calculate that R optimum, it wants you to find the corresponding height. So what is the height that we are going to do? All right, so let's start. Let's start by start with the first function. Let's do. Remember, the lower part is the lower part will be the cylindrical part, and the hemispherical part will be the higher. All right, so start a new script, and he has given us the volume, which is 600 cubic meter, and that volume will include both the cylindrical part and also the hemispherical part. All right, so let's start with the function, and we want to find H first as a function of that volume that he's given us. So H, which is the height. We'll do another function for the cost, but for now we just want to do the height. So well, we're going to have to use two functions in this case. So first, we're going to call this the height. And that should be as a function of v and r. Okay. We don't know r yet. We know v. He's given us v, but we don't know r. And this is where we get r, the optimum r, from the cost function. But before we do this, let's put the equation of that height. The height should be equal to, let me open a parenthesis here. The v, which is in this case, it's the 600 cubic meter, minus, I'm gonna just remember there's a volume, there's hemispherical volume. So let me let's subtract that hemispherical volume minus pi, or actually 2 pi, right? Yeah, 2 pi, 2 times pi times r, and don't forget the dot, to the power 3. So this is the volume of the this is the volume of the hemispherical, and just you have to divide this by 3. So that is, if you minus the volume of the hemisphere, you're gonna be getting the volume of the cylinder, right? Because remember, the v, the total v, let's just v should be equal v of hemisphere plus v of cylinder. Okay, and v of cylinder is equal h. If you go back here and here, let's see here, he's given us that. That is equal to pi r squared times h, right? So h times pi r squared. So I'm trying to solve h in here. And v hemisphere is given us that, which is 2 pi r, 2 pi times, I'm missing an r in there, times r here. What is that here? We made a mistake in here. So it's 2 pi times r cubed. I don't know why this came up. All right. So 2 pi times r cubed over 3. Okay. And then that's close the parentheses. All right. So this is 2 pi r cubed over 3. Okay. Plus. So that's why I am minusing this when I bring this, and then I divide it by pi r squared. So now we're going to also do the division. So back in here to this equation, dot, and this is pi times r, again, don't forget the dot square. Okay. So again, I got this from this equation here. The V total volume of the tank should be equal to the volume of the hemispherical part plus the volume of the cylindrical part. And I am just solving for H in there. Right? Just look at this here. You will know that, again, this is H. So this is the cylindrical. Sorry, this is cylindrical. Cylinder. And this is hemisphere. Okay? And the total volume will be the sum of both. So, and let me just end this. Go back in here and end this. And I'm gonna save that one. Let me save that one as height and just leave it there. So that is saved. So what I want to do now, I'm going to start a new function, because now I'll be calling this function when I solve for h after I get r. So let us start a new function with cost. So function, remember we're optimizing the radius of this based on of the tank based on the cost of the how much it's going to cost us. So that is cost. This is what we want to calculate, and I'm going to call this tower. You can call it whatever you want, tank or whatever. R. Okay. And again, R, it will be the input variables, and cost will be the output variable. So H in this case is equal to height, right, of 600 and R. Very important to understand what I'm doing here. So I'm calling a function within a function. So that function here, cost, is calling also the function height that I just saved. And remember, function height has two input variables, which is the volume, and because it has a volume and it has the radius as well. And so I don't have to rewrite it, retype it. I'm just calling that function in there. And I don't need to, let me do that. I don't need to show the results for that. I'm just going to go and put the cost of that. So the cost is equal to, again, it says 800. Let's see here. It is 400 per square meter for surface area and 600 per square meter. So it is 400. Let me write this. So it is 400 times 2 times pi, right? And then 2 pi r times h, so times r times h. So that is for the cylindrical part, right? It's $400 per square surface area plus times h. Let me just, don't forget to do this here, dot. Every time, forget that, that will not work because you're dealing with array. So plus 1200, or in this case 600, okay, plus 600 times 600 times it's saying 2, what is that here? Let me see here, per surface area. So it's 2 times pi. Just make sure. Yeah, 2 pi r squared. So 2, where is that here? 2 times pi times r, and don't forget the dot square. Okay. So let's see what we did here. And let me just do this one here. I said cost, it's $400 per surface area for the cylinder. Again, the cylinder circumference area is 2 pi r times h. So that takes care of this cylinder right there. And the cost of the spherical, hemispherical, you see it is 600 by 2 pi r squared. So we're just doing whatever he's asking us to do. He's given us the equations, we're writing that. And I'm just going to end it now and save it. So I'm going to save that as, well, I'm just save it as the defaulted one, tower. I'm just going to keep that safe. Okay. So how are we going to use those two functions? Well, this is what we want to do. I'm going to go to the command window and let me enlarge that command window, because this is where I'm going to call these two functions. So the first thing I want to do is I want to find the optimized or the optimum R optimum, where this cost uh, will be minimized. Okay, so R optimum, or I'm just going to call optimum, and underscore R is equal to F M. Set to use the minimum bound B and D. So it's optimum is going to be the minimum of the tower cost, right? Because we're trying to do the, so this is where you use the handle function at, and I'm going to use the tower because this is what function, which is the cost, that is the cost equation. So I want to minimize that between, let's just do the R between, I mean, you can just put the limit any way you want, but let's just do it from 0 to 100, right? I mean, you can do it 0 to 500, doesn't matter, but let's just do 0 to 100. This is the boundary, you know, for R. Remember, R is a function. The cost is a function of R, right? So, so let's call that and see what that will give us. So it's F minimum. It's going to give us the minimum of that function between 0 to 100. So let's do that. So that's what we got is 4.8572 meter. Okay, so that is the optimum radius where we have the minimum cost. Okay, remember what we did. We're using this command fmin bound, but we're calling that function tower, which is the cost, right? The function tower is the cost, function cost, and we're optimizing the radius based on the minimum cost. Now, what we want to do, we're going to find what is the minimum cost. So minimum cost, right, is equal to power, right, of optimum R, because that cost function is the power function of optimum underscore R, right? And that's it, minimum cost. So it's going to cost us 1.4823 times 10 to the power 4, almost like $148,000. Okay, so that is, and the last thing, I don't think he asked us for that, but that's fine. We did that. Now, if he wants to find what is H, and this is part of the design, how he's going to design the cylinder when we optimize the radius. So in this case, you're just going to go back to optimum. You're going to go back to the first function that you did. So optimum H, you're going to call that height function, which is height, right? The height function, and we are going to say that it is 600. Almost. Yeah, 600. Okay, it's a volume, which is 600. And the optimum radius, which is optimum R. And then just to, that would be 4 point, all right, so well, something is not right here. All right, just do 500 here. Something is not right. Okay, let's read this problem. The radius that results in the least cost compare corresponding height All right, so let us suppose we did this 500. Let's see what we got. Yeah, 3.508. So that's based on 500 cubic meter. So based on 600 cubic meter, you get 4.8. Based on a 500 cubic meter, you get 3.508. So really depending on what you're trying, in this case, it has 600. So that will be the optimum H, and it changes if you change that volume. Okay, so very good. So this is both of our functions working fine. So let's summarize what we did. Let's go back and see what we did. So we did two types of function. That is minimize. All right. Let's open those. The first one was the height function. I'm just going to open it. So that was the first one, and which was a function of the volume given and radius. And remember, we said that the total volume is equal to the hemispherical volume plus the cylindrical volume, and we had to calculate H as a function of that volume and R. And that was it. This is the function, and this is what we want from that height function. And we did the second function, we did the tower function. And the tower function is, it tells us how much it costs based on that radius. And he's given us those equation, for the cost, and it is a function of R. So in this case, what we did, since H is a function of R as well, so you will see that we called another function within the function H, because in order for us to calculate the cost, remember there's an H in here that needs to be calculated. So we called H, which is another with a height, with another function within that function to calculate the cost. And now when we go back in here and see what we did, he said to use the fmin bound, and all we did, we used that fmin bound, and this is the function that we use, the handle function tower, to minimize it. So we want this, when this is minimum, that function is minimum between 0 to 100, and it is going to be minimum for that optimum R. So that's where we calculate R. Then we did the minimum cost, which is we call the tower function. Remember, the tower function is the cost function. And then at the end, you can calculate the H using the height function. Okay, so very straightforward, a great example, because there's two functions in there that we worked with, and we call again a function within a function, and we optimize the radius based on the cost. Please do that also as well in your own, and again, you can always slow down when you play this recording if you cannot catch up with me. All right, so let's move to the third or fourth problem here. So let's see here. So this is the third problem. Let's read that one. Using estimates of rainfall, evaporation, and water consumption, the town engineer developed the following model of the water volume in the reservoir as a function of time. Okay, so the volume of with a function of time is 10 to the power 9 plus 10 to the power 8, 1 minus e minus t over 100 minus RT. Now, V is the water volume in liters, T is the time in days, R is the town consumption rate in liters per day. All right, two user-defined function. The first function should define the volume for use with the F0 function. The second function should use F0 to compute how long it will take for the water volume to decrease to X% of its initial value of 10 to the power 9. And the inputs of the second function should be X and R. And test your functions for the case where X equal 50% and R equal 10 to the power 7 liter per day. Okay, so very interesting problem. The volume is a function of time and also function of the rate of use or the consumption of rate for the town per day. So what we want to do, we want to write two functions, and these two functions we're going to use also the F0 functions to calculate for the time of the water and also for the X for the decrease of the percentage of the decrease of the volume as well. Okay, so let's start with, now we're going to start a little bit with the first function, which is the volume function. So I'm going to actually enter this function, the one that is given to us. This is what I want to start with. And so we know that volume function, or delta V in this case, because it is a changing of volume, because that's what we are interested in. So let's do that. So let's minimize this one here. All right, so let's clear here, CLC, and let's start a new function. Now, I'm going to start with the first function, which is function here. All right, the function time, function delta, I'm going to call this delta V. Okay, delta V, which is the change of volume, is equal to volume. That is the name of the function. And I'm just going to put it as a function of t. Okay. All right. Let me just to make it more visible. And I'm going to actually, what I want to do is something that you guys always should do when you're trying to resave your input, even the output parameters or variables. You want to move them from local, which is within the function, to the global, which is going to be in the workspace. So I'm going to actually do global, but I really want to use this later on with the another function when I call it. So R and also X. So these are R and X. I'm going to make them a global. Again, global means that you're taking those variables after you do the calculation or when you input those variables. You're not just going to use them for that local function. You're going to actually save them in that workspace memory right there. So that's done. So let's put the volume. Volume is equal to the equation here. So it's 1 E plus 9. So that's 10 to the power 9 plus 1 E plus 8 times 1 minus exponential of minus t divided by 100. Let me close this parenthesis. Minus r times t. Okay. So 10 to the power 9 plus 10 to the power 8 times 1 minus exponential minus t over 100. Guess I'm missing, no, minus r times t. All right. So delta V, the change in volume, equal to V minus 0.01 times x. X again is the percentage of the change of the volume times x times the original volume is 10 to the power 9, so times 10 1 e plus 9. Okay, so it is the percentage, the volume, the original volume, right, minus the percentage of again the value, which is 10 to the power 9 here, liter. Okay, so again, x is the percentage of the drop of the volume in liters. So right, okay, let me just do this one here. So again, it is visible 0 here. Make sure that I enter everything right. Okay. All right, let's just save that. I'm going to save that as volume, leave it in there. Now what I want to do is I want to start a new function, and I want to do the new function will be the decreased function, because this is what we want to call the function time. So we want to calculate the time, so equal to decrease, that is the name of the function, of x and r. It's a function of the use of the consumption and also the reduction, the percentage of reduction of the volume. And again, we're going to do global Rx, right? And then we're going to here solve for that. Time 0 time is equal to F0, right? And I'm going to call the volume function, right? I'm going to call, so I'm going to use the add, the handle, and volume. This is what I'm trying to apply the F0 on that volume. Now, in this case, when you do F0, you want to specify a value that's close to where the function is when you're trying to calculate those roots of that function. All right, when f is 0, you want to calculate that time. So I'm just going to put 1 for now. And that should give you something which is a close. I mean, it doesn't have to be close. It's just a number that it will start the iteration for us because the F0 function, the way it works, and this is something we'll probably explain later. Most likely we're going to explain later. And when we try to calculate, even trying to calculate the roots of the function, or you're trying to say where is that function is 0, you always want to determine a value or specify a value close to where that function is 0, and then it starts, MATLAB start that iteration from that value that you're given. But it doesn't matter, it doesn't have to be pretty close to it. So, so pretty much that's it. You're gonna just put here into my column. It's something like I said, the F0 and fmin bound and fmin search, all of these functions, we'll be using those later on. And we'll talk about how MATLAB came up with these functions, because all these functions, there's a written code behind them, and we'll cover that later on in the semester. So let's save that. Again, save as. It will give you directly decrease. I'm going to save that. And now we're going to go to the session and see how we are going to calculate the time. So, and it's telling us to try that. That is C. Test it for x equals 50 when the reduction in volume 50%, and R is the use or the consumption is 10 to the power 7 liter per day. So I'm gonna go in here and I'm gonna say time is when I be equal to the decrease function, right? And remember, decrease, it has the reduction of 50%, so that's 50. R is 50, or X is 50, and R is what did he say? 10 to the power 7, so 1 e to the power 7. Okay, and notice that when I typed decrease, automatically MATLAB is giving me a hint here that there's two values that I need to enter, because this particular function that I created, it needs two input values in order for it to execute the equations. So when it says time decrease, if I open the parentheses, automatically telling me that there's X and R in there that you need to enter values for. So I'm just gonna close that and then hit enter. So time is 54.182 days, because this is time days. Let's see what the warning is telling us. It's interesting to read, even though it did the calculation, but there was a warning. So the value of local variables may have been changed to match the globals. Future versions of MATLAB will require that you declare a variable to be global before you use that variable. In decrease line 2, warning the value, same thing. Okay, so you can probably do the variable global Rx before you do the calculation. That's something you probably want to do. So remember, if you go back to the equations with the global after the function, you can probably start with the global Rx, and you will get rid of that message. But anyways, it did the calculation, and as you can see that there's two stages that this command went through. First of all, if we go to the time that we want, if you look at the command, we said time, which is equal to decrease. So we call this function here decrease, and decrease function, there's a function within that function, because time is equal to F0, and I'm calling that volume function that I created here, right? So this is the volume function with delta V, to calculate delta V. And what we did this at R. If you look at R, yeah, when we if you look at that, for that F0, the time that we solved, if you go back to that, there's a time variables in there. We set it start with 1, t equal 1 day, but then it starts iterating these equations until you find it split the time And from there, when it did this, it F0 it to that volume. And it gives you that time, okay? And again, this with a decrease of 50%, right? Decrease of 50% of the original volume. And also, this is the consumption per liter for the tank, okay? So you change that, it will change the time in there. So all it did actually, if you had this function, and this is an exponential function, and all it did for us, it just calculated the value of R when this Vt goes to 0, okay, or delta V goes to 0. That's exactly what F0 does to us, okay? F0, that means that function is 0 at these roots. All right, so we're gonna actually revisit, like I said, F0, Fmin bound, Fmin surge, all of these, we're gonna revisit those and explain how MATLAB came up with these equations, those built-in functions that really required a lot of coding to come with this, and you will see the power of MATLAB. The power of MATLAB, and just by a small command that it does all these iteration for us, and it gives us something that probably is going to take hours and hours to solve. All right. So again, we'll just like you to definitely do whatever I'm doing, and there's a couple more problems that I wanted to do. I think that, yeah, there's a function within a function that I want to do. Let's see what we're going to do next time. So this is done. We want to do this one, use a primary function with a subfunction to compute the zeros of this. And the last problem is we want to create a anonymous function of this to plot the function to determine the absolute location, its minimum, and also we're going to use the fmin bound function to precisely determine the location of the minimum. So two more problems that we're going to do next time, and I'm hoping that we do these two problems. And then we move to another section, again, all these reviews where we are going to start talking about writing MATLAB programs, again, using the if functions, else functions, and some logical commands that is pretty much very useful in engineering. So we'll stop today, and we'll continue working on more problems next time, and probably we'll start the lecture again for those if and if else functions as well, logical functions. Thank you very much, and we'll see you in the next lecture.